Welcome back to Codex. Today's speaker is Afonso Bandeira from ETH Zurich. Professor Bandeira is an expert in the mathematics of data science, and today he'll tell us about random matrix theory. Take it away, Afonso.
Thanks, Dustin. Thanks for the introduction. Thank you all for coming, and thanks to all the organizers for the invitation. It's a pleasure to give another codex. So I'm going to tell you today about random matrices, the intrinsic freeness phenomena, and how it can give you all of us sharp non-asymptotic inequalities. I'm mostly going to be focused on the work that with wonderful collaborators that are listed here together with the papers. And just as a note, please ask questions all you like. I'm happy to, I don't know what system you use, but I'm happy to get diverted. It's going to be mostly handwritten so that it stays flexible. So I'm happy to be diverted and to stay a bit later to after to answer any questions or discuss or anything. So, okay, so random matrix theory, let's get to the actual content. So the question is, what's the typical spectrum of a matrix with random entries? Right, and this goes back at least to the 50s. So, and it was when Wigner wanted to understand something in nuclear physics, he had to understand eigenvalues of a very complicated operator, and he had the in hindsight brilliant idea of saying, okay, this operator is very complicated. What if we just pretend it had random independent Gaussians? And he realized that the statistics of the eigenvalues look like the statistics of eigenvalues he wanted to understand, and the rest is history. Then maybe something that seems like a more natural idea is to look at, say, if you get data and you look at sample covariance, your data is random, so your sample covariance is going to be random. And so you might understand eigenvalues to see how close you are to the true covariance in spectral norm. And so Mashenko and Pasteur described the law of this, and Wischer already in 1928 already described not quite the law of eigenvalues, but rather the joint distribution of the entries, but he was definitely talking about a random matrix, just not about its eigenvalues. There's a few very nice stories. I'll just give some bullet points, but von Neumann and Goldstein asked themselves, what does the conditioning number of a typical linear system look like? Right, and so you have to understand something about eigenvalues of some whatever typical is, so some random matrix. And there's this beautiful connection with number theory that if you look at what the zeros, for example, what the zeros of the Riemann zeta function look like at the critical line, the statistics of them resemble the statistics of zeros of eigenvalues of random matrices. This even created a lot of excitement that maybe this could be one way to attack the Riemann hypothesis connected to the so-called Dilbert-Polya conjecture. And there's lots and lots of other applications. I'll pick a couple to be illustrative later on. Okay, so the sort of canonical object in random matrix theory is so-called a standard Wigner matrix. Okay, so it's a D by D symmetric matrix with Gaussian variance 1 over D entries. Okay, so everything independent except for the fact that it's symmetric. And if you try it on the computer and you look at the eigenvalues, so at the histogram, the nice picture to do is to look at the histogram of the eigenvalues. You see that it will have this very nice picture of what we call a semicircle. So we'll look just like a semicircle for -2 to 2. Remarkably, there's no eigenvalue running away. Okay? But, eigenvalue, and there's you can study all sorts of things, how quickly you converge to this, what to do if you zoom in here, what to do two eigenvalues look like near each other, what does the law of the spacing, all sorts of things. In this talk, I'm more interested in trying to understand models that are different. So models that are called structures. So they're not necessarily IID models. And just to convince you with a very sort of silly example that other models of random matrix can have eigenvalues that look very, very different. Just take a diagonal matrix, right? Just take D diagonal with dii entry say 0, 1. Okay, so Gaussian 0, 1. If you look at eigenvalues, you're just going to get the entries in the diagonal. So you're just going to get a Gaussian, right? The eigenvalues are going to look like a Gaussian. In particular, the eigenvalues will run away, right? There'll be eigenvalues running away as in this case, D goes to infinity. So now to study sort of general classes of random matrices, the tools are a bit different than classical random matrix theory, where you study very precisely models like the standard Wigner matrix. But there's very nice inequalities. Many of you maybe have interacted with some of them. So they usually go by the name of matrix concentration. So let me show you some examples. So matrix concentration inequalities. Okay, so maybe the first theorem of this type is, I would say, is what we call non-commutative kinship. Okay, so I'm going to call this NCK. So this goes back to Louis Picard and Pizier in the 80s. And in our language, it says the following: that if I have X, a matrix, so a D1 by D2, okay, it doesn't need to be symmetric or self-adjoint. What it needs to have is jointly Gaussian entries. So every entry is Gaussian, they can have any covariance, and they're jointly Gaussian, right? Any linear combination is Gaussian. And let's say mean zero. I mean, mean zero is not terribly important, but let's say to make things simpler now. Then the following is true. So the expected value of the spectral norm of the matrix, so is always between this parameter sigma and up to a constant, a root log. Let's say d1 plus d2, okay. Sigma. Okay, and what is the sigma? The sigma is the following. So this sigma is sigma square is equal to the maximum between this quantity and this quantity. Okay, maybe you've seen these inequalities. If you write, right, any matrix with joint Gaussian entries, you can always write it as sum of GI, where AIs are deterministic and the GIs are AID. It's the exact same thing. And if, just to make things easier to see, if X is self-adjoint, then sigma square is just a more familiar expected value of X squared. And the remarkable thing here is the matrix can be very, all sorts of dependencies. The norm is up to at least a log is given by this parameter sigma. Now, just a bit of housekeeping before we continue. So here I didn't make matrix self-adjoint. It doesn't really matter. Throughout the talk, I'm going to go between considering matrix to be self-adjoint or not. The reason is that you can reduce to self-adjoint or symmetric matrix very easily by what's so-called a Hermitian dilation. So this is a very nice trick to know. So if you have a matrix X that's not self-adjoint, the singular values and minus the singular values are basically the eigenvalues of this one, which is now self-adjoint. Right? Meaning you can, if what you're trying to study is eigenvalues of non-symmetric matrices, it's a whole other story. But usually in the downstream applications we want to understand, we're interested in understanding singular values of non-symmetric matrices, and they're just the same as understanding eigenvalues of symmetric matrices. Now, something that's more, doesn't need Gaussianity and has been a lot more useful.
Sorry, I have a
Yeah,
question. So why do this rather than just looking at X star X or XX star? Like why lift it up to the higher dimensions?
yeah, because you want to keep things linear. Maybe this will be more, right? So in particular, for example, I mean, the way you prove this theorem, okay, I'm not going to prove this theorem. I mean, I can if you want 10 minutes. I need 10 minutes after the talk is over. I can show you the proof of this theorem. But the way you would prove this theorem, you actually assume it's self-adjoint and just prove it for self-adjoint. And then you plug in this matrix here. And you see that the sigma for this, okay, let me put something that doesn't, right? So if I plug in sigma, if I do expected value of this matrix square, I get exactly the maximum between these expected values. So the way you prove these theorems is you assume it's symmetric, and then you plug in this matrix. And if you plug in XX star, right, you would get some term of order 4 that you would have to now control. So potentially, or XX star wouldn't be also wouldn't be jointly Gaussian.
Thank you.
Yeah. Okay. So good. Okay. So just two more pieces of housekeeping. So one is, an inequality that maybe many of you have used is matrix Bernstein. So it's also something of this style. So this is due to Oliveira and Trop. And Joel has a wonderful monograph describing many of these inequalities. So if X is here not necessarily jointly Gaussian, not jointly Gaussian entries, but a sum of independents. So where Xi are independents, like a matrix, like a Bernstein inequality, say D by D, and let me say self-adjoint. Again, Hermitian dilation can take this away. And let's say the maximum eigenvalue is smaller than R, right? Like in normal Bernstein, you get an inequality of the following type. The probability of lambda max, sum of xi, bigger or equal than t, is smaller or equal than d, times, and then something that looks just like, if you remember what Bernstein looks like, it's exactly the same, right? 2/3 are t. Now I want to convey two things with this. Or three things. One I can't convey, but you just have, for those of you who know, you'll know, the other ones should trust me, that this is extremely useful. There's lots and lots of places where this inequality is useful. I can give some examples later. The other thing, now the two things I want to convey is that this dimensional factor here is actually the same dimensional factor. So this dimensional factor here is the same dimensional factor as here. Right? Because, the t, right? This t, if you were to try to move the d in the t, it would go inside the exponential and inside the square would look like a root log. Okay? So it's essentially the same dimensional factor. And the other thing is that these inequalities look a bit different because it looks like this is a tail bound while this is just an expectation bound. But I would argue in reality, this is an expectation bound under these kinds. So if you were actually wanting to get a tight tail bound, what you would do is you would use this inequality to get a bound on expectation, and then you use a concentration of scalar random variables to get concentration on this quantity. Something like Gaussian concentration in this case, or some other concentration inequalities in other cases. Okay. So in particular, we will focus on controlling expectations. Then classical concentration inequalities work to then get concentration, right? Because then we're talking about just classical, real valued random variables, not matrices. Okay, so now sometimes when I give this talk or versions of it, I actually show the proof of non-communication because I want to show you other things. I'm going to not do that now. But I want to explain to you where this dimensional factor comes from and where the gains to remove it can come from. And so I'm going to tell you a little bit about Gaussian analysis. Okay? So the thing that sort of governs a lot of what's going on is something called Wick's formula. So I'm going to write Wick's formula and I'll try to explain it. Okay? So and I know that some of you have watched my other versions of the talk, so hopefully this way you'll get something new out of it. So even before the end, where there will be some new things. So Wick's formula says that it's a way of organizing calculations of moments of Gaussians, right? A very convenient way of organizing calculations for moments. Okay? And so if I have, you should think of it this way. If I have, say, an assignment from 2p to n, and I have n, say, IID G1, Gn, like n01 IID. Now let's say I look at the expectation of G of U1, G U2, and so on. Okay, this looks like a bit of a silly thing because if I have something like that, I just ask how many of these Gaussians are actually the same, and the others are independent. It's just splits into products of moments of each one of these Gaussians. It's just go look in the table what the moments are. But there's a very convenient way of organizing that calculation, and it's the following. You take the sum over all pair partitions. Okay, so what this means is all ways of partitioning 2p elements into pairs. And now you ask how many of them are compatible with that choice of a partition. Okay. So right, for example, let's say, let's say P is 3, just to get a picture. One possible pair partition would be this. And say another possible pair partition would be this. I'm just putting, whenever two things are in a pair, I'm just linking them with a little arc. And now say an assignment that's compatible with this one is U1 goes to 1, 1, 1, 1, 2, 2. And this goes, it could be 1. Well, this one is actually compatible with the exact same thing. Right? Okay, is the definition clear? Now, in a sense, what makes these dimensional factors show up is the fact that there's a lot of pair partitions, right? There's like kind of exponentially many, right? Because for each one of, as I try to build them, for this one, I have a choice of basically 2p minus 1, and then, this gets assigned here. For this one, I still have a lot of choices and so on. That's kind of where it comes from. And so let me try to convey this in a bit of a different way. So let me write this. Let this be a pair partition. Okay, so a splitting of 2p elements in pairs, and let mu u of mu be sort of the assignment or an assignment that u is compatible with this partition and with no other. Okay, so it's like an assignment that actually only takes things to, there's only collisions of size 2. Okay. Then another way of writing this formula is that expectation of GU1, GU2, GU2P is equal to 1. I mean, it sounds a bit silly what I'm saying, but bear with me. Okay, now comes the interesting thing. Let's say that instead of Gaussians, I take standard Wigners. Okay, so let's say I take now W1, W little n, they are now n by n standard Wigner matrices, just like the definition before. Now I ask the same thing, right? I have a partition, and now I ask for an assignment that's compatible with only that partition, and I ask, what does that moment look like? Okay, and there would be a matrix, so the right way to look at it is by the normalized trace. So now I ask, what is the normalized trace? So when I write the trace with the little t, I mean trace over dimension, right? Average of the eigenvalues, not sum. Right? Okay, my question is, what is this? Okay, so I would argue that, okay, first observation, if I take, maybe it's good to just remind everybody, if I were to take something like W1 squared, or any of the W squares, this is just identity. You don't have to do the calculation in your head, just me, but if you take expected value of a matrix square is identity. Okay? So I claim that if I take, say, this crossing, then the value is 1, right? Because when I take this crossing, right, if I take this crossing here, I can sum inside over this and I get a 1, and this becomes an identity, and then I can sum over this part and come out, peels off another identity, and then peels off another identity. Okay, so this is equal to 1 if my crossing is such that I can peel off parts of it. I can peel this off and then peel this off and so on. Okay? So what we call such crossings that can be peeled off is non-crossing. And the magic happens if we have a pairing like this, where I cannot peel off. And when I can't, actually there are cancellations. And this is going to be O of, say, O of 1 over dimension. Dimension here is begin, if U is crossing. Okay, and this is where cancellations arise. So when matrices are sufficiently random or behave sufficiently uncommutatively, you expect that when you take moments involving them, there's a lot less terms. If I now ask you how many partitions are there on uncrossing, right? Believe me, that is just like opening parentheses and closing parentheses in these Catalan numbers that maybe you remember studying back in discrete math class or something. And so this is where the cancellations are going to arise. And so in this story, there'll be sort of three characters or three main characters. Is our matrix X, which I'm going to write in this way with the G's, just because it will be easier to describe the other characters. Okay. Then there's going to be the one where I'm going to make the object non-commutative by design, by wanting to compute moments in this way rather than this way. And so I'm going to call this xn. And this is going to be, okay, I'm going to change the order just because it's more convenient. The tensor products of AIs with WIs. It's like a matrix where instead of putting Gaussian entries, I put Gaussian matrices in the entries. And as this big N goes to infinity, there is a certain limiting object that lives in, that lives in the theory of free probability, which I'm going to call X free. Right? I won't talk much about. Where these are so-called semicircles. There's some operator that corresponds to the limit as n goes to infinity of the big N matrices as they get bigger. And big N goes to infinity. Okay, so far everything clear? Now comes the story of freeness. Okay, so we have these players, these characters, xn, and x free. Back in the 90s and early 2000s, there was the discovery that as n goes to infinity, this object starts looking like that one, right? Relating for n large, relating these two objects. That's what's known as asymptotic freeness. So the object on the right was not defined as the limit of xn, was defined as an object that satisfies certain algebraic properties that are a bit like the free group, right? They have no more relations. It's like they have no more relations than what they would, yeah. It's but basically like the free group. They have no more relations that were just designed by the generators. And this was work of Inequalities. And then very important work, depending on what kind of convergence you consider, very important work of Agarup and Torbjörnsen. And why did they care about this? It's because this object X free, it's understanding it is very important in understanding of von Neumann algebras and certain questions in operator theory. And by showing that these objects are related, you're effectively showing that certain von Neumann algebra, certain objects in operator theory are reasonably well approximated by finite dimensional objects. And this prevents them from behaving too wildly. And so you can prove theorems about these objects. Okay, so one of the central questions in this field is if I take the free group on two elements, and now I consider what's called the von Neumann algebra, so a certain closure of the algebra generated by the regular representation on that group. The question is whether I do that for the free group on two elements or the free group of three elements, whether they're isomorphic or not. So this is a central question there. And this theory was developed to attack these kinds of questions. They succeeded in some, not in that particular one. Yeah. And the phenomena I want to tell you about today is a different phenomena. And it's about these things already being quite close. So of x1 already looking like xn. And this is what we call intrinsic freeness. And this is our work and what I want to talk to you about today. So I work together with Marc Boisiardo and Ramon van Handel from 23, and then a certain lower bound by myself, Cipollini, Schroeder, and van Handel this year. And there are theorems that look like this. So I'll show you the theorem that already includes the two papers together. They'll look essentially like this. So here's the theorem. The probability that the Hausdorff distance, so just think of it as the different distance between the two sets of the spectrum, so the support of the spectrum of X and of X free is very small, right? So the probability that this is big, I'll write what the terms actually look like, but I need to say what these things are. Okay, I'll try not to write a lot of these things. I'll just do it once. And smaller equal than exponential of minus t squared. Okay, where, what do I need to tell you? So here x doesn't have to be mean zero. X just needs jointly Gaussian entries. And sigma of x is just the norm of expectation of x minus expectation of x squared. And v square is the covariance. So the spectral norm of the covariance matrix of x, so now it's the d squared by d squared object, and sigma star is small. Okay, I'll just, smaller than either sigma or v. And so it tells you that if you understand the spectrum of this free object, where there should be a lot more cancellations, X should have a spectrum that's essentially the same. And on the technical side, now more want to tell you about applications, but on the technical side, basically this first paper, what we showed is that spectral statistics of this object and this object, or this object and this object are essentially the same. And then what this paper does is shows that spectral statistics of this object actually describe the spectrum. That feels kind of a weird thing, but the point is that you still pay a price, like on your error bounds, you pay a price of the amount of smoothness in your spectral statistics. And while this is a D by D matrix, there could be one runaway eigenvalue, but it needs to have weight at least 1 over D, right? There can't be, at least, even if there's runaway parts of the spectrum, its weight needs to be at least 1 over D, so there's some amount of regularity. Why this is some infinite dimensional object could potentially have runaway mass of the spectrum with exponential or double exponential small weight. And so spectral statistics of reasonable smoothness would not see it. And so you need a regularity theorem on this object. That's what this does. Okay, that's sort of technically what happens, but I won't discuss it very much. Okay, so now let me tell you the kind of things that you can do with it, and then I'll go into application. Okay. So one is, lambda max, maybe I won't write the formula if anybody wants to see. So lambda max of x free can be computed. Like it's no longer a random object. X free is an infinite dimensional operator. You can compute its norm. Something called Lehner's formula. It's some variational formula. I'm not saying it's easy, but it's a completely deterministic thing. It's a deterministic object. Okay, and in particular, say if the expectation of x is 0, you get relatively easily theorems like this, that x free is at most 2 sigma and at least sigma. There is no log factor. And so you immediately get theorems like expected value of x minus expected value of x is smaller or equal than 2 sigma plus some error term that will be smaller. So the point is you should be using these inequalities. Okay, should have said this maybe to be more clear. You should really be using these inequalities when v is a lot smaller than sigma, right? That's when they're meant to be used, because this is meant to be an error term. So you should use them when this happens. Okay, and I'm focusing here on Gaussians, but the work of Tatiana Brailovskaya and Van Handel can do universality. So I use universality. basically relate sums of independence with a Gaussian version of it. Maybe I'll just write X Gaussian. So once you understand matrices with jointly Gaussian entries, you can understand also sums of independence. And you recover Bernstein, potentially without log factors, depending if the V parameter is small.
Afonso, what does V look like in the case where I have a diagonal of Gaussians?
Good. Okay. Yeah. Probably I should have said this already. So V of, say, the Wigner matrix. So let's just compute it together. What is it? So it's just how much what is the norm of the covariance of the entire matrix? So the entire matrix is basically independent entries, except each entry shows up twice, right? So the covariance of that vector is just is essentially like a diagonal matrix with twos in the diagonal, because it's a d square by d square matrix, right? And so V square, meaning that's the square. So V square is 2, not 2 because we normalize by 1 over d. So it's 2 over d. So it's much smaller than sigma. In the case of diagonal, right? So V square of the diagonal example, well, then it's just all the other entries are 0. In the diagonal, they have variance 1. And everything is independent. So V is just 1. So it's exactly the same as sigma. You do not expect to see any freeness. And indeed, the eigenvalues do run away. So yeah, thanks. Yeah. Good.
Is it weird that I'm getting a 3/4 power on log?
Yeah, it's probably not the right power of log.
Do you
Yeah,
expect it to be 1/2 or?
so for example, if matrices are independent, have independent entries, you can go to 1/2. 1/2 should be the right thing. There's some good reason of why, in this sense, 1/2 seems difficult. I can discuss a bit in the end. The thing is that, yeah, maybe I can say the thing is that this is getting a lot more than the spectrum. It's getting that it behaves like S3 as an algebraic object, meaning when you take objects of this type and you multiply them together, they should still behave freely. And so if I have matrices like a Wigner tensor with an identity of the same size and an identity tensored with a Wigner, spectrally wise, they still look very Wignery, right? The eigenvalues just show up many times. But when I take these two objects, they actually commute. And so they don't behave, algebraically, they don't behave freely at all. And yeah, this is somehow an obstacle. Okay, maybe I'll just say this. Does it help?
Yes. Do you have a handle on what capital C is?
Oh, I have no idea. I would imagine it's not so bad, but I don't know. But typically you would use this theorem in situations where really, I mean, in most situations you would use it. V is probably even polynomially smaller than sigma. Yeah, I'll show you a couple of examples. Yeah. Okay, so one thing is it can, one kind of, I think, surprising thing is that this theory is not just able to upper bound spectral norms, but it can see spike models. It can see the so-called BUP transition. So, for example, if I take a model, so if I take a model like X, say lambda, where I get lambda VB transpose plus W, a standard Wigner, and say V as norm 1, right? This is the typical like signal plus noise type model. And you ask, can you see the signal in the middle of the noise? We know that this can be seen as soon as lambda is bigger than 1. And we know what the largest eigenvalue of this matrix looks like. This is the so-called BUP transition. But if you were to take sort of a triangle inequality type approach, you would say, well, the norm of this is like 2, right? Remember, there was it's this 2 basically. The norm of this is 2, the norm of this is lambda, so whenever lambda is bigger than 2, you should see something. But actually, you see something at 1. What happens is, even though sort of this, the spectrum of this is between -2 and 2, by putting a spike somewhere here, it pops out, because the noise pushes the signal and you still see it. But this is a very fine phenomenon, like a very fine-grained phenomenon. You can see this with these tools. So if you compute using Lerner's formula, lambda max of the free analog of lambda of x free of x lambda, you do see that this is 2 if lambda is smaller than 1, and it's lambda plus 1 over lambda if lambda is bigger than 1. Right, and the spectrum looks, in this case, looks like this, and then there's a little ball here, right? Because they're no longer, it's an infinite dimensional object, it no longer has just a one eigenvalue. So, okay, so now I want to tell you about some applications. So how much time do I have?
Let's call it 12 minutes.
12, okay. So, okay, so if it's 12 minutes, let me skip the application and show you just the downstream part of the application. And then I can go back to it if there's time, because there's an idea I really want to show you. So there's many, let me just, give the 30-second explanation of the application. So the application had minus tensor PCA. I'm happy to discuss it in the end. But when you have problems in high-dimensional statistics, a very natural class of algorithms, or a very important class of algorithms, is sum of squares algorithms. Right? They're very general way of attacking problems. And one way to try to prove that these methods work is to prove that whatever bound you want to give is provable within the proof system of sum of squares algorithms. And so I'm going to just show you an example of such a proof. Okay, so I'm going to skip some things I was going to show you, and I'm going to go straight to this, and then I'll go back just to make sure I have time to describe it. Okay, so this is screenshotted from Sam Hopkins' PhD thesis. Okay? And it's, I don't want you to read this carefully at all. It's just that what you have to control is that you have to give an upper bound to the injective norm of a random tensor, right? Something that's like the max over, so the max over x in the sphere, say, of this quantity here. And the way, and you have algorithms to do this. In particular, the sum of squares hierarchy, the sum of squares hierarchy gives you an algorithm to do this. Okay? And you can prove that these bounds are better than whatever can be proven used within the proof system of sum of squares. And so what is stated here is a bunch of steps taken in this proof system. So in this proof system, you're allowed to do Cauchy-Schwarz, because if you remember the proof of Cauchy-Schwarz, you do it by setting a square bigger than 0 and then expanding. So basically, proofs of that type are within the sum of squares, proof system. And so if you carry down this proof, and lots of the proofs are like this, in the end, you have something that, some norm of x, right? You imagine x is equal to 0, and then you have some quantity that depends on your tensor. And then if you want the result, say, with high probability the sum of squares hierarchy works, what you need is to upper bound, say, with high probability, the norm of objects that look like this. And in this world, almost always you get things that, involve polynomials of matrices. So in this particular case, the problem is that you get, so I'll show you, right? These T's are big matrices. So the problem that you have to solve is WY, say W1 through WN, are D by D matrices, standard Wigner. And you have to understand, say, expected value of the norm of the sum, right, from 1 to n, of WI tensor WI. Say minus this expectation. You have to understand objects like this. And so objects like this, they're not like the matrices from before, right? Because they involve polynomials. Right? Now the entries of this matrix are polynomial, like each of these WIs is Gaussian random variables, and now you take squares. And so I want to tell you about a theory to understand spectral norms or spectrum of matrices that are built by taking polynomials of random variables. Okay, so let's go back to that. So we call this matrix chaoses. And I'm going to do it for degree 2, but what I'm going to do works for any degree. So let's write it like this. I have x equals sum. There'll be two summands, say I and j from 1 to n, and I have gi, gj, aij. Okay, where g's are now my ID. Right. And let's say no I is the same as j, like what we call square free, okay, or diagonal free. Okay, now we want to understand this object, right? Aij is say a D1 by D2 matrix. And let's take D to be the maximum of the two, just because I'm going to need this number a bunch of times. So the question is, how do you understand the norm of this object? So the first thing you do is there's these standard decoupling tools. So the norm of this is if there's no diagonal term, the norm of this is the same as a decoupled version of it. So first decouple. So what is a decoupled version of it? I take the sum, say I, j, 1, n, and I take gi and hj, where now the hj's are themselves IID from the first ones. So now this is a different matrix, but their norms up to a constant are the same. This will help us. Okay, so now comes the idea. Well, let's take this matrix. Here's a nice way to organize it. I can take it as the sum from j from 1 to n of hj, sum from I from 1 to n of gi aij. Now I can call this my bj. Now I just have a version of, if I condition on the randomness of the g's, I can just use non-commutative Kinship, right? If I can condition, I can freeze the randomness of the b's, and now what do I have, or of the g's? And what I have that the expected value, right, of sum aj ej is smaller or equal than, let's say, root log. And now what do I have? I have the max between, sum, no, not sum, sorry, expectation, sum, b, bj, bj transpose, say star, and bj star bj. Right? Okay. So now I have to, right? So this is the expectation of this with respect to the, with respect to the h's. But I still need to take an expectation with respect to the g's. Right? In order to make this work, I would still need another expectation with respect to the g's, right? And so I would have here some expectation with respect to the g's, and so on, right? But this seems problematic, right? Because now I have a quadratic term here. But look, if you see, so okay, I forgot a square root here. What is this? This norm here is the same thing as just taking the norm of b1. This norm to the square root is just the norm of what we call a flattening. If I just make the matrix where I just put blocks b1, b2, and so on, the norm of this is the square root of the norm of that, because that thing up there, this thing here is literally this times this transpose.
You're
right?
concatenating these blocks in a
Yes, I'm
short matrix.
concatenating the blocks. Yes. So now I have a, D1 by n d2 object. And over there, what do I have? Well, I have the exact same thing, but going down, right? And so a much more productive way of thinking about non-commutative is that it's actually the maximum between these terms. Okay, all these blank pages, sorry. But the maximum between these two terms is actually just, it's somewhat linear. It's not really quadratic. It's, right, I mean, once I take the square, is just the maximum between taking the flattenings of the matrix coefficients downwards or as rows or as columns. Okay. But now if I have it this way, I can iterate. Right? Because now what do I have? All I have is the expectation over G, right? Of say, okay, I'm going to be, because I'm not caring about constants, the max could just become a sum, so I'm not too worried about this. I get root log D, and then I get what? The max between expected value over G of this matrix. But what is this matrix? This matrix is just sum of GI, and then what do I get here? I get AI1, AI2, and so on, all the way to AIN. And the other so-called flattening. Okay, this is hard to, I1, I. Okay, it's a lot of notation, kind of terrible notation, but there's not much going on. Is it clear?
I think the GI wants to be to the right of your sigma, but otherwise, yes.
The GI wants to be, yes, definitely, not underneath, yes. Good, thank you. Okay, but now I can just do non-communication again, right? Because now, let me copy. Because the idea, this is the idea. It's almost done. If I do non-communication again, what do I have? For this sum, I now have to take this matrix and flatten it out further, either like this or like that. And for this one, I have to do it either continuing like this or like that. And so in the end, what I'm going to get is I'm going to get the expected value of x, which will be the same as y, is what? To do another non-communication, I pay another root log. So I get log d. And then I get the max between four things. I get the max between flattening row, row. So, okay, let's do it. A11, A12, blah, 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 blah. I get doing it A11, A12, A21, and so on and so forth, all the way to ANN. There's another square one, which is doing A11, A21, A12, and then so on to ANN. And there is the big one to the, not, sorry, it fits there, good. You know, okay, it's a lot of writing, but you see what I'm doing. Okay. So in reality, what I have is a theorem for any Q. What I have is a theorem of the following type. It's what? I get a log, you can see easily, then I'm going to get a log d to the power q over 2, however many times I have to do non-communication. And then I get some sigma parameter, or what I'm going to call this, which is the maximum over all these flattenings. And this is optimal up to the logs, meaning like this, expected value of x is actually up to a constant bigger than sigma of a. So you're getting the right answer up to logs. Okay, now one more magic and then one smaller idea. This v parameter is also a flattening of sorts. Because let's look at what this v, let's say x is just sigma of gi ai. What is v? V of x is just, v square of x is just the norm of the covariance of x. What is this? This is just, so once I take the square root, this is just what I get if I take vec of each of the matrices, as a vector. So it's just like taking my data, right? I have some kind of tensor data, which is my matrix and index by which, right, A11 is a matrix, A12, and so on. V just corresponds to taking flattenings where I break the matrix dimensions. Right now the matrix don't get, right here I took 4 flattenings, but a matrix stayed a matrix. Here a matrix is no longer a matrix, now is a vector. And so you now have this theory where you take all possible flattenings. If the ones that destroy the matrix are small, asymptotically smaller than the ones that keep the matrix, instead of iterating non-commutative Khinchin, you can iterate these strong inequalities and have no dimensional factors. Meaning you can develop a theory for these, what we call matrix chaos, without having any dimensional factors. And this is optimal because this is the right answer. Now, what I want to convince you very quickly is that even though this looks horrible, computing this is actually easy. So do I have like 2-3 minutes to show you one calculation, or should I not?
Do it.
Okay. All right. So here it is. Let's take the original example. So, okay, you have to do the decoupling a bit carefully in the WI case because there is a square term, but that square term is easy to deal with, so I'm just going to ignore it. So after decoupling, I'm just showing you the interesting part. There's some non-interesting things that need to be done. For decoupling, what you have, let's look at this example. So after decoupling, the Wigners now here are independent from these, right? I just did the decoupling step. Okay, let's write this let's write this. Okay, we just need to be brave. So what is this? This is the sum I from 1 to n, and now I need what? I1, I2, K1, K2 from 1 to d. And what do I have? I have Gi, J1, K1, Gi, J2, K2. And then I have, right, these are just my entries of the Wigner matrix, so I have n of them. So these guys run from 1 to d. And now what do I have? I have a matrix that just puts a 1 in entry J1, K1, and a J1, J2 tensored, and the one, and sorry, I'll just write it because it's hard to say without writing. So it's just a matrix that E is just a matrix that puts a 1 in this entry. Right, what is the Kronecker product? It just puts there in the entry J1, J2, K1, K2. Okay. Now I have to take flattenings of this. It looks horrendous. I'm going to show you very quickly that it's not. So let's do another step. So sum, and I have the same sum of the G's. And now this E, I'm going to write it differently. I'm going to write it as canonical G1, tensor, canonical G2, tensor, canonical K1 transpose, tensor, canonical K2 transpose. Okay, now let's take a flattening. So one of you, pick a flattening. Which one do you want to be the row coordinates and which one do you want to be the column coordinates? So it's 2 dimensions, right? So you pick, well, you can pick row, 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 column, column, row. Just pick one while I'm writing.
Column row.
Column row, good. So let's take the flattening. So let's take the flattening where the first, columns are, so I take, so column row, so I get 2, and so column row, so 2, 3. So because, right, the first, yeah, let me just write like this. So 2, 1. So the 2 goes as a column and 1 goes as a row. Let me write it like this. Okay. So what is this? What does it mean to take a flattening as a column? It just means that I'm summing with E transpose to whatever is the index. Right? So all I'm doing is if I take the first one as a column, I have to take E, I, J, K1 transpose and sum over all of this. But in reality, all this is just taking the indices that show up here and doing EI transpose, EJ1 transpose, EK1 transpose. And now the one is going to be a row. EI, EJ2, EK2. And now I copy that. Let me be lazy and just do it like this. But now look at this sum. I mean, okay, this looks horrendous. Can anybody already see that it's really not? Think about what the norm of this object is. This is just summing a matrix that has ones in certain places with a very special tensor structure. If I have, first of all, I can change the order of these things and it doesn't matter for the norm, right? I'm just reindexing. So I can change the order. These objects are now, fully commutative with respect to the norm. And if I have something like EJ1 and EJ1 transpose, let's say I have a one EJ1 transpose and an EJ1, it's just the same thing as summing over EJ1, EJ1 transpose. So I'm going to have just an identity in the end. Right? So these terms completely cancel. These terms, say
You're
this
saying you're
term.
now changing the norm by permuting the factors? Is that the
Yes.
point?
Yeah. By changing the order. As long as I change the same on every summon, of course. Right? These terms will just look like sum EJ1 transpose, which is just an identity. So those go away. Then if I have, okay, let me see if I have more colors. If I have, say, EI transpose EI also goes away. Now, if I take EK1 transpose, this stays. But the norm of EK1 transpose is the same thing as just having one EK1 transpose. Okay, so let's make another thing. This guy stayed. And EJ2 and EJ2 also stayed. And EK2, they went away. So in the end, this norm is the same as sum over what survived, the J2 and the K1 of EJ2 tensor EK1 transpose. And the norm of this, these sums are from 1 to D. And so the norm of this is just going to be root D times root D. The norm of this is just D. So the norm of all these objects, when you have this kind of tensor structure, all you need to do is to see how many times things cancel. And you can do this extremely quickly by just looking at a table. So the choice that you made was column row. So you pick this choice. And there is a way to write this table just by counting. I mean, this, if I told you the algorithm, this takes 10 seconds to do. You get this square. This is the square, the norm square. You get this square. So you just do this for all the flattenings. And in this case, because these ones are always smaller than those, we get that the norm of this object is the biggest of them. So it's ND square. And there is no log factor because these are smaller. And this works for any, okay, to be able to run the algorithm, you need the coefficient matrix to be of this type. Every single example we've seen in theory of computer science, that's the case. And okay, this was the last idea. I'm probably over time, so I'm happy to answer questions. Stick around to talk more, but I don't want to take anybody else's time more than I'm allotted to. This was the last idea that I wanted to convey.
Very good. Let's thank the speaker by clicking buttons.
Thank
And
you.
I'll stop the recording here.